Okay, lesson 2.4. We have mentioned a little bit about the idea of differentiability. Differentiability being, if you differentiate something, that's taking the derivative of something. Differentiability means if something is differentiable, you can take the derivative of something. Okay, so here we are connecting differentiability and continuity. How they relate, when one exists, when the other one exists, those type of things. So, first thing, as we connect differentiability and continuity, determine when derivatives do and do not exist. So in this lesson, we'll investigate the relationship between differentiability and continuity. Our focus will be to determine when a function fails to have a derivative, because if it fails to have derivative, it's not differentiable. Okay, it does not have differentiability. Big word. Now, a function that is differentiable as a point, differentiable at a point, is also locally linear at a point. So it can have a derivative. It can have a slope line drawn, okay, a tangent line drawn there. The graph, in order for a function to be differentiable at a point, the graph must be continuous at that point and smooth at that point. If something is not continuous, it's not differentiable at that point. Okay? You can't take the derivative at a point when it's not continuous. If it's not smooth at that point, thus our sharp, hard points and our cusp, then we can't take the derivative at that point. And those are the two big places that we fail on differentiability. So, differentiability at a point. A function, f of x, is differentiable at a point c if and only if. Basically, that's saying the limit of, it's the limit from the left equals the limit from the right. But what is that limit? That limit is the definition of derivative, right? That's our alternate form. But that's basically saying that if a function is differentiable at a point, then the limit from the left and the limit from the right are the same. And that is the big thing there. Okay? And limit from the left, it's the limit of the slope. And the limit of the slope from left and right. So basically your derivative from the left and derivative from the right have to be the same. And that's, the big thing of when hard points are differentiable, their slopes aren't the same for both sides. Now, so how the derivative may fail to exist. Following examples will show us how a function will fail to have a derivative at a point where there is and here are your options, corner, cusp, vertical tangent line, or discontinuity. Those are ways that it will not be differentiable because you can't take the derivative. So, given the graph, f of x equals absolute value of x minus 1. Absolute value means you're going to see a v, right? As an algebra reminder, the minus 1 in the absolute value is going to take my graph to the right. That's all good stuff to remember, yes? So, what is f prime of x as x approaches 1 from the left? Thoughts? Negative 1? Because what are we asking here? F prime of x says what is the slope, right? When you see f prime of x, slope of the tangent line. I just always shorten it to slope. But what is the slope as we approach 1 from the left? So basically, what is the slope over here? And the slope of that left side is negative 1. Okay? What is f prime of x as x approaches 1 from the right? Now it's a positive 1, correct? Is f continuous at x equals 1? Can I put my pencil down and draw it in one big swoop? Technically, you don't have to pick your pencil up to draw a V, do you? Okay. If we go, that's my, before you get to calculus definition of continuity. You guys, as calculus, we're supposed to think the limit from the left equals the limit from the right. Now, when we talk limit from the left, limit from the right, I'm just talking the limit of the function. Do these pieces of the v converge at the same point? Yes. Does that point exist? So is it continuous? Yes. Okay, so this graph is continuous. Is it differentiable? What reasons why can you tell me no? Okay, it's a hard point, yes? That's the physical, thing we look at. The algebraic part to look at, the limit of the derivative. When I say the limit from the left and the limit from the right here, it's the derivative. Are the derivative on the left and the derivative on the right the same? No. Okay, so I agree, hard point is the obvious. Officially, what I need to remind you of, though, the limit from the left, or the derivative on the left does not equal the derivative on the right. Okay? And I'm going to write this a little official here. I'm going to kind of squeeze it in. Since the limit as x approaches 1 from the left, and I'm going to say of f prime of x, okay, does not equal the limit as x approaches 1 from the right of f prime of x. There is no derivative. And I would say there is no derivative at x equals 1. When we say no, this is not differentiable. Realize we're not talking about the entire function, are we? We are just focused on, is it differentiable at x equals 1? That's the only piece of this we are talking about here. The rest of this, it's differentiable every place else, except at x equals 1. Okay? Okay, example 2 if you're ready. Given the graph, f of x equals the cube root of x. So a connection. Are you guys connecting? So x cubed is that, yes? So what's the cube root of x? That flips sideways, right? So that's a good graph to be familiar with, okay? So given the graph of cube root of x, use the alternate form of the derivative shown to show the function has a vertical tangent line at x equals 0. So, there is no way, well, I don't know, maybe there is. Okay, I'm trying to figure out if I'm going to get this. So, as we do this, the limit as x approaches, what am I going to use for c? We're talking about 0 here, yes? So the limit as x approaches 0 of f of x, what is f of x? Cube root of x minus f of c, which in this case is going to be f of 0. So cube root of 0 over x minus c, so x minus 0. Well, clean it up. The limit as x approaches 0. What's another way to write the cube root of x? X to the 1/3. I have my reasonings. So on top we have x to the 1/3. Cube root of 0 is 0. Bottom, x minus 0 is just x. X minus 0 is just x minus 0. X. Now, clean this up. X cubed divided by x. What?
X cubed divided by...
Oh, sorry. Is that what I said?
Yes.
Okay, try again. X to the 1/3 divided by x. This right here is what I want you to do. Yep, when you have bases are the same, and there's exponents and you're dividing, you can keep the base and subtract the exponents, yes? That's the way we could write it. Because 1/3 minus 1 is going to be negative 2/3. And where do we keep a negative exponent? In the denominator. So the limit as x approaches 0 of 1 over x to the 2/3. What do we get when we do direct substitution? One over 0. Okay. Huh? Well, think of this if this was your slope, because that's basically what we're doing here, right? When you got 0 in the bottom of a slope, what were we always taught? What? Undefined or no slope, right? Undefined is the idea here. That this is saying that our slope right there is undefined. Well, a slope that is undefined is what type of slope? It's a line that is vertical. What were we supposed to show? We're supposed to show that there is a vertical tangent line. Well, we got a number divided by 0, or a number divided by a number getting closer and closer to 0. And so that is an undefined slope. Okay, so that's saying that there would be a vertical tangent line there. Okay. Notice on both of these examples, my graph was continuous, yes. But on both of them, they failed to be differentiable for some reason or another, right? Or at least at a specific point. Okay, keep that in mind. Given the graph of 1 over x plus 2 squared, so that's what the graph looks like over here. Okay, you've got that asymptote because it's x plus 2 squared. Both pieces of my graph are going up. Describe the derivative of f as x approaches negative 2 from the left and the right. So, I always have to think carefully here. As x approaches 2 from the left. I'm not writing this as a full limit here. I guess I could, but as x approaches 2 from the left, we're talking about the derivative here, right? So as we get closer and closer to 2 from the left, so as we're on this piece over here, right? What do you know about f prime of x? That should not say equals, I just realized. That really should say approaches.
Is it -2?
Yeah, it should be -2, isn't it? Sorry, the negative and 2 are spaced out on a separate line, so when I went to grab the number, yeah, definitely -2.
Why wouldn't they just write -2?
I don't know. Okay, thoughts? What is f prime of x doing? Huh? Increasing? Okay. Increasing in terms of, what do you notice? F prime of x, we're talking slope here, yes? Derivative. What do you notice about all the slope along here? First of all, it is always positive or negative? Positive, yes, because this is an increasing graph, so my slope is always positive. As this line gets steeper and steeper, my slope is getting bigger and bigger. So what's my slope going towards? Positive infinity is what we'll explain that as. Now, as x approaches -2 from the right, what is my derivative approaching? What do you notice about all the slopes on the right side? All these slopes are what? Negative, yes? Because officially, if we go from left to right, this is a decreasing graph, right? So all my slopes are negative. Now, as we're getting closer and closer to 2, if we forget the negative for a moment, what are the slopes doing? The slopes are getting bigger, right? But we're in negatives, so they're getting bigger in the negative direction. So what is my derivative approaching here? Negative infinity. Does it ask it in the next part? Based on what we just talked about there, what does that tell me about this graph at negative 2? It's what?
It's not different.
Okay, well, yeah, because we're looking at the limits of the derivatives. First of all, it's not continuous, right? But then also it's not differentiable, yes? So this is one, and I don't really have room. I'm just going to say, therefore, not, I'm just going to say not diff at x equals negative 2. And that's because my derivative from the left and the limit of the derivative from the right are not the same. Okay. Given the formula f prime of x, use the formula to evaluate the derivative when x equals negative 2. So here, again, basically we're doing the same problem, but we're doing it algebraically. Okay, so we're looking at the formula, so we're looking at the slope, and we're going to look at it when x approaches negative 2 from the left, and when x approaches negative 2 from the right. So let's do f prime of negative 2 from the left. In other words, if I'm trying to investigate the derivative from the left of negative 2, what should I plug in here? Negative 2.1 works for me. So I have 1 over negative 2.1 plus 2 quantity. That's not supposed to be a squared, is it? Cubed. So I have 1 over negative 0.1 cubed. And we don't even have to necessarily do the math.
Is it negative 2?
Okay, wait.
Did they copy it down?
Okay, wait, what? Oh,
One says squared, one says cubed.
no. This is a slightly different equation. I grabbed the 1 from up above because I did. And, okay. So that's on me. I grabbed the wrong value. Now, it's supposed to be negative 2 on top. Here's the deal, guys. You don't know the shortcuts yet. We could do the definition, but the original function is f of x is 1 over x plus 2 squared. This is f prime of x that I'm looking at. This is the derivative function. So the derivative of 1 over x plus 2 squared is this negative 2 over x plus 2 cubed. Again, it'll make more sense when we get to our shortcuts. Okay? I looked up at the I grabbed the wrong equation, so that's on me. That's fine, because I did have a squared here originally, too. That's fine. Got it. Okay. Now, the important part there is the negative, because you've got a negative 2, which is a constant, right? Divided by negative 0.1 to the third. So negative 2, here's what I need to think. It is a negative, yes? And you could even think about it being like a large number if you want. Compared to our denominator, so negative 0.1 to the third. What do you know about a negative to the third? It's a negative, right? 0.1 to the third is going to be a small number, right? if we approach negative 2 from the left, this number in the denominator is getting smaller and smaller and smaller, right? So if you have a larger number on top dividing by a smaller and smaller number on bottom, what are we approaching? Infinity. And since it's a negative divided by a negative, that's going to be a positive infinity. Okay? And this is a large number divided by a small number. Here's what you need to be thinking. I put the negatives to indicate it's a negative divided by a negative. Okay? Now, coincidence? As x approaches negative 2 from the left, according to the graph, it was positive infinity. As x approaches negative 2 from the left, in the equation, it's positive infinity, yes? Not a coincidence. We're just looking at it 2 different ways. So now we're going to evaluate our derivative as negative 2 approaches from the right, which means what kind of number am I plugging in? Negative 1.9 plus 2 to the third. Still negative 2 on top. Really the only thing it changes, instead of negative 0.1 to the third on bottom, it's positive 0.1 to the third. So I'm going to have a negative, a larger negative number, or just a solid negative number, divided by, what do we know about 0.1 to the third? It's positive, and it's going to be getting smaller and smaller and smaller, right? So a constant number divided by an ever increasingly smaller number is going to take me to negative infinity. Yes? How did I get what? Negative infinity here. So this was as we look at the left. And first of all, we have to identify that all this piece right here that I have traced in red, those are all negative slopes there. I know they're negative slopes because anytime I would draw a tangent line, it would have a negative slope, or this is a decreasing graph, so I know it has negative slopes. As we get closer to that asymptote, my tangent lines are getting steeper and steeper and steeper. So we think about those slope values getting bigger and bigger and bigger, but since they're all negatives, they're getting bigger in the negative direction. Does that make sense? Okay. Okay. What did we just come up with here? Again, not differentiable, yes? Same thing we talked about earlier. The whole point here is that the derivative at negative 2 does not exist, whether you go from up here or whether you go from down here. We got the derivative from the left and the derivative from the right are not the same, so the derivative does not exist. Thus, takes us back to the not differentiable idea. Okay. Big box. Important box. Differentiability implies continuity. If a function is differentiable at a point, then the function is continuous at a point. So notice what it says here. If a function is differentiable at a point, then the function is also continuous at the point. And that is the idea of differentiability implies continuity. If you can come up with the fact that something is differentiable, then it is also continuous. You don't even have to check for continuous or continuity. That just sounds weird. You don't have to check for continuity if it is differentiable. That is an automatic, I don't want to say assumption, I don't know, I don't have a good word there. Maybe I should say assumption, but it's a definite. Okay, so if a function is differentiable at a point, then it's continuous at a point. So differentiability implies continuity. Something that is differentiable is continuous. Now, the opposite of that. It is possible for a function to be continuous, but not differentiable. We saw that on the previous page, didn't we? We had a couple that were continuous but not differentiable. So you could be continuous but not differentiable. So continuity does not imply differentiability. You can't say, oh, it's continuous, so I know it's differentiable. You can't do that. You have to prove those two separate. But if it's differentiable, you can say, oh, because it's differentiable, it's continuous. You don't have to go through a proof of continuous. Okay? So continuity does not imply differentiability. And where are things not differentiable? Sharp corners, cusps, vertical, tangent lines, or discontinuity. Those are all things that are going to make our graph not differentiable. Okay? Okay. Write the contrapositive of the following statement. Have we worked with contrapositives? I know not in calculus we haven't. Oh, it probably does take you back to geometry. It probably was in geometry. I don't know. I'm not saying you remember it, but valid point.
That was freshman.
Because here, I know. Well, because here's where my brain was going with this. I don't think I teach it pre-cal. I know I don't teach it in Algebra 2. Where I've taught in the past is in our Saxon calculus book, it reviewed it. There's a spot it reviewed it. And that was always a really easy lesson. So we reviewed contrapositives, converses, and inverses. Okay, so dig back to your geometry brain.
I know it's geometry because I've been helping Tyler on this.
Okay, well, I'm trying to think, when did you learn this? But no, that's right. You learned it in geometry. Okay, so, Mrs. Rogers. Dig way back, right?
It's a long time ago.
Okay, so contrapositives. If a function is differentiable at x equals c, then the function is continuous at x equals c. Does anyone remember how you write a contrapositive?
No.
Okay, so contrapositives, you take the two pieces, you flip them, and you negate them. Does that make sense when I say that? So you flip the order. So the if and the then pieces flip. And, so whatever the if was becomes the then and vice versa. And you make them both negative. So basically you throw the word not into both. That's what a contrapositive is. Okay, so this said if a function is differentiable at x equals c, then the function is continuous at x equals c. So we're going to take the last part first. If the function, and I want to negate this, so I'm going to say is not, and what do I want to say? I'm grabbing the ending, so not continuous at x equals c. Then, now you grab the beginning and you also make it negative. The function is not differentiable at x equals c. Maybe there's a glimpse of familiarity in there. I don't know. Maybe not, right? If I recall, and you know what, here's my deal. As I was doing this last night, this was my guess of what it was before I checked myself. I was so proud of myself. I knew which one the contrapositive was because I don't teach it. So I'll be honest, I forget it too. Okay? But if I'm not mistaken, the contrapositive, is that the one where the contrapositive, if the original statement is true, the contrapositive is always true, I think? You guys, okay. Blank looks. Okay.
I remember there's something about that.
I'm pretty sure the contrapositive says if the original statement is true, then the contrapositive is true. Now, if you look at it, if a function is differentiable, then it's continuous. That's our whole differentiability implies continuity. If the function is not continuous, then it's not differentiable. Well, that's true, because you can't be differentiable if you're not continuous. So, I'm pretty sure the contrapositive is guaranteed to be true, though. Okay. Example 4. Describe the x values at which the function, there's the equation, there's the graph, is differentiable. Justify your answers. So I want to know, where is this graph differentiable? My answers are in interval notation, if that helps. What are we going to have to know?
What did we just do? Continuous?
I don't know, we've done both. We've done continuous, we've done differentiability today. We're focusing on differentiability. Okay, looking at the graph. What do you know about the graph?
It looks like a W.
Looks like a W, okay? Good observation. Do we know anything about differentiability of this W?
It has like
There's 2 points where it's not differentiable.
Okay. There's 2 points where it's not differentiable because they are sharp points or cusp, whatever you want to call them. Okay. Well, if I'm being asked to write the x values where it is differentiable, I need to know what those x values are to exclude them. How can I find those x values? Where are those pieces of the graph at?
zeros.
They're zeros, aren't they? In other words, they're on the x-axis. So if they're on the x-axis, that's when y equals 0. So set your equation equal to 0. And I basically would ignore the absolute value. You don't really need to, because you'll get what you need without worrying about absolute value. If I set x squared minus 5 equal to 0 to find my zeros, x squared equals 5, and x is the square root of 5. But when you're in an equation setting, to take the square root of 5, you say plus or minus. Do those pieces look like they could be at square root of 5 and negative square root of 5? Yeah, I don't know what the square root of 5 is other than it's 2 point something. So that sounds like a good ballpark to me. Okay, so where is my graph differentiable? Where's my graph start being differentiable? Think interval notation here. Where's my graph start?
Negative.
Okay, it's coming from the left, negative infinity. It is differentiable from negative infinity to where?
Negative square root of 5.
Okay, my first breakpoint is at negative square root of 5. Parenthesis or bracket? Parenthesis, because that square root of 5 is not included, right? Because at square root of 5, it is not differentiable, so it's not included. I'm going to say union. Where's my next piece of the graph start? Negative square root of 5, which again is going to be a parenthesis, comma. Where's my next break? Positive square root of 5. And of course, that's going to be with a parenthesis, union, ran out of room, we'll go down below. Next piece is square root of 5 to infinity. Now, it did say to justify. I mean, what was the key here? G of x had sharp corners here, didn't it? Okay, so just going to make note of that G of x has sharp corners, sharp points, I don't know what you want to call them, at x equals plus or minus the square root of 5. There's really not enough room there. If your guys' notes weren't so long, I could load in the pages twice and have a top half and a bottom half, but your notes are so long and I never know how far I'm going to get that I only get 15 pages here. I have to be able to make it through Algebra 2 and Pre-Calc throughout the day also. I know, I would prefer a few more than 15 because
30?
it makes it rough. At least when I teach 3 different classes throughout the day.
RAM upgrade.
So, huh?
I said RAM upgrade.
I don't know if that's a RAM upgrade or what that is. Okay, let's see, where am I at here?
Don't ask.
Huh?
She doesn't even know what you're talking about.
Oh. I just don't know if that would necessarily connect with RAM or not, but I don't know.
I mean, it seems like it could.
Yeah, I don't know. RAM being your computer, what do I want to say, memory? Is that the word I want to use?
I think it's random access memory.
Yeah.
It's like the one that like is your short term, like you're using currently.
Yeah. General word memory. And what is this BenQ? It is a big computer, right? Just like what is your cell phone? Your cell phone is a computer,
It's
you
like
know?
you have like so many like apps open or whatever, eventually it'll slow down, but once you X out of it, it'll speed back up. That's your RAM getting bogged down.
The one that always got me was the time I went to the cell phone store because my cell phone just would not connect to the internet for whatever reason. And I went in there and they said, have you restarted your phone? No. Well, like, it's just like a computer. You have to restart it every so often. It's like, really? That's what... So, you know, it was one of those things. It's been a few years. Can I say that? You know, it hasn't been recently. Okay. Example 5. I don't know if I can get through this or not, but we're going to talk about it. Find all the values for which the function is differentiable. Where are the problem areas going to be?
At 0, and 3.
You see that? Okay. We want to check the problem areas. And on a piecewise function, your problem areas are going to be where the breaks are, right? So my problem areas, I'm going to find in that section there. And so in this case, my problem areas are going to be 0 and 3 that I need to check. I'm not saying they won't work. I'm just saying we have to check them. Now, okay, sorry, I was trying to decide how I wanted to do this. If this is differentiable, we first need to figure out, is this equation continuous, yes? If it's continuous, how do we know if it's continuous at 0? Yeah, the limit from the left equals the limit from the right. So, what is my left piece? Left piece at 0 is going to be x plus 1 squared. The right piece is going to be 2x plus 1. I'm skipping writing limits. I probably should officially be writing limits, but plug in your 0, yes? When you plug in 0, what are we finding? Plug in 0, we're going to get 1 equals 1. So what's that tell me? At x equals 0, my graph is at least continuous, yes? Okay, let's also check x equals 3. So at x equals 3, the left of 3 is 2x plus 1. That has to equal the right of 3, which is 4 minus x squared. Do the math. What do I get? Seven equals 1. Okay. So, is it continuous? Not at 3, but it is at 0, yes? So, what do we know for sure about differentiability? It's definitely not differentiable at 3. 1, it could be, and it is. And it'll be easier to explain that when we know a little bit more about quick derivatives. Okay? At this point, I would just kind of, if you think about x plus 1 squared being a parabola, 2x plus 1 being a line, we know it's already continuous. It should be able to flow and be a decent graph there. Okay, and I'm going to leave it there. So, the question was, where is the function differentiable? All values of x. What values of x is this differentiable for? What would you say? What? Okay, all of x except 3. So if I write that in interval notation, it's negative infinity to 3 and 3 to infinity. Okay? So what else did I have? I guess I should. That is where h of x is differentiable. Okay? And then right here, we know that this told us there was a discontinuity at x equals 3. Okay? That was the information we were able to give. Okay. I think my watch is behind. My watch only says 12:30, but what's iPad time?
12:30.
Oh, okay. I think my clock is just slightly off then. See, there's no point really going into the next one. So, again, we're looking at piecewise functions, though. So, notice what it says. They're always challenging. So, we will talk about those tomorrow.